Hey guys, this is Joel. Hope you guys can really sketch those curves well. Okay, that's it for me.
All right, here we go, guys. Just like you heard Ms. Vidal, let's see if we can sketch these curves because it's called curve sketch. LOL. All right, let's do it. Um, why does this have a 1 on it? All right, let's just do that anyways. Okay, find vertical and horizontal asymptotes, guys. Horizontal asymptotes are simple. That's whenever the limit is approaching infinity. So I'm going to make x approach infinity of this function, positive and negative infinity. So I see 2x over x, so I see 2. And I'm approaching negative infinity now of this function. And again, I get 2. So the horizontal asymptote is 2. And then vertical asymptote, wherever the denominator is on, wherever this function is undefined, and it's undefined if x equals -5. So I look for that, guys, and here we go. I'm going to make this red marker a little thicker. Yeah, that's better. All right, here we go, guys. Let's continue. Find the vertical and horizontal asymptotes of this guy. So again, horizontal asymptote, the denominator is larger than the numerator. So if I approach positive infinity, I will get 0. So it looks like y equals 0 is a horizontal asymptote. If I approach negative infinity, well, you can't approach negative infinity because I have a square root here. Now, I can factor this out in the bottom. So in the bottom, x squared minus 12 squared root of x plus 36, that's the same thing as square root of x, square root of x. And let's see, the only way to get 36 is 6 and 6. So there it is, and I want to add up to a -12, so they both have to be negative. So I have a vertical asymptote at x equals 36, guys. So vertical asymptote at x equals 36, because that's where this function is undefined. So here we go. Hopefully that made sense to you guys. If it didn't, ask me and I will go into more details. Let's go to the next question. Find vertical and horizontal asymptotes. Because this has sinusoid behavior, guys, it's just going up and down, 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 up and down. This is not going to have a horizontal asymptote, so no horizontal asymptote, but it does have an infinite amount of vertical asymptotes. Whenever sine x minus 1 is 0. So sine x minus 1 equals 0, move the 1. Where does sine x equal 1? Well, it equals 1 at pi over 2. And if I do a revolution, I'm still back at that same location. So plus 2 pi n. In case you're wondering, you're like, well, what are you talking about? I'm talking about the unit circle. That here's where sine x is 1. And if I do a complete revolution, I'm back at the same location. So pi over 2 plus 2 pi n is my vertical asymptote. It has an infinite amount of vertical asymptotes, guys. All right, let's continue. Determine whether or not the graph has a vertical tangent or vertical cusp. Okay, this is actually pretty interesting, guys. I got lucky with my quiz that I didn't have any that had vertical cusps. Without putting these in the calculator, I want you to be able to tell algebraically whether it's a vertical tangent or not. And it's very simple. If you have a function, a derivative, and let's say it's like, I don't know, I'm just pretending, like 1 over x, and I approach 0, so limit as x approaches 0. Well, okay, the only way you can get a derivative of 1 over x is if the original function was ln x. But let's pretend for now that it's 1 over x like that. If I can approach from the right-hand side of this derivative function, and I get, let's see, if I approach from the right-hand side, that's a positive infinity. And if I approach from the left-hand side of this function, and I know that you can't approach ln graph from the left, but just bear with me, guys, and you get negative infinity. So this would be an example of a vertical cusp. For it to be a vertical tangent, I must be approaching right and left, and it has to be the same behavior, guys. Now, it doesn't have to just be a positive infinity, negative infinity. It could also be like absolute value. Let's say my f prime is something like absolute value of well, my original is like absolute value of x. Simple. So my f prime is either going to be a positive 1 or negative 1. So f prime of x, because my original function with absolute value of x is it's going to be a piecewise 1, -1. and it's 1 for x over 0 greater than 0, and it's 1 for -1 for x less than 0. So on this one, if I approach limit as x approaches 1 from the right of f prime, you get 1. Limit as x approaches 1 from the left of f prime, you get -1. So again, this would be a vertical, actually that would just be a cusp. That would just be a cusp. And that's it. So that's what we're looking for, guys. And of course, for the vertical tangents, you just have a derivative that's undefined. So hopefully that was a super fast lesson on how you know algebraically if you have a vertical cusp or vertical tangent. I will be doing this in class, guys, giving you guys further breakdown on when you have vertical tangents and vertical cusps algebraically without looking at the picture. For now, if you need the assistance of a calculator, I guess that's fine, but try to do as many as you can without a calculator, guys. So, all right, let's keep going. So now let's just talk about how to do this question. So here we go. I'm going to take a derivative because it wants to determine whether I have a vertical tangent or vertical cusp. So f prime of x is equal to, let's see, 5 times 4 is 20 over 3. X minus 3 raised to the power 1/3. Okay, so now, because I have a 1 critical point at 3, so let's see, this is a smooth transition, so I just have one vertical, sorry, it's not a vertical, I just have one critical point at 3. It's a smooth transition. This derivative is never undefined, it's always defined, so you have neither a vertical tangent or a vertical cusp. All right, let's go to the next one. Hello, Ms. Moreno. No, I'm not talking to myself. I'm making a video. Okay. LOL. All right, here we go. Determine whether or not the graph of this function has a vertical tangent or vertical cusp at 0. So I'm going to take a derivative. So let's see, 4 times 3, 4, 8, 12. So 12x, and I'm going to subtract 1. 12 over 5, sorry, guys. 12 over 5x, I'm going to subtract 1 from that 3/5. So that's going to be a negative 2/5. Minus, let's see, 3 times 6, that's 18, so 18 over 5x to the negative, nope, that's going to be positive, dummy, to the 1/5. I'm going to do, well, first let's go ahead and rewrite this. So 12 over 5x to the 2/5 minus 18 over 5, I guess x to the 1/5 up here. I kind of want to do, I can already see that I have undefined whenever x is 0, guys. But I kind of want to do, let's see, what do I want to do? I'm going to move that x to the 1/5 down. And I'm going to do, well, okay, it doesn't matter. It said x equals 0. So let's just go ahead and just evaluate it. Sorry, guys. So I'm going to write, here's what I'm going to write. Limit as x approaches 0 from the right of f prime. If I approach 0 from the right, this here is going to be a huge number. It's going to be a huge positive. So if I have a huge positive, who cares about this guy? Because look, it's x to the 1/5, so I'm going to be subtracting some small number. So it's a huge positive divided by some small number. So it looks like I'm going to have positive infinity. If I approach 0 from the left, I'm going to have, again, a huge positive number. So again, I'm going to have positive infinity. Now, I know you're saying, Chavez, how do you know that you're going to have a huge positive number? Notice or recognize that I have to square it first, and then I take the 5th root. So it's x squared. So if I approach 0 from the left, it's going to be a really, really, really small number. I'm squaring it. A really, really small negative number. Squaring it, it's going to turn into a positive. And then I take the 5th root. So I'm going to have a super small number in the denominator. Some number divided by a super small number is an infinite. It's a big number. So big minus some small, I'm going to have a huge positive number. So if you don't believe me, guys, try it out. Put in like insert x value of negative 0.00001, square it, take the 5th root, multiply by 5, and then do 12 divided by that number that you get, and you're going to see you're going to get a really big number. So hopefully that made sense to you. Because both are approaching positive infinity, I have a vertical tangent. Here we go. Let's go to the next one. I'm going to take a derivative again. So let's take a derivative. F prime of x is equal to, let's see, I have that negative there. So negative 3/7, 3 minus x. I subtract 7 over 7. So let's see, 3, 4, 5, 6, 7. So a negative 4/7. So again, I have a negative 3 over 7, 3 minus x to the 4/7. So because I have an even number there and then 7th root, it's going to be the same deal again, guys. So limit as x approaches, and I'm going to approach 3. If I approach 3 from the right hand side, so of f prime, let's see what we get. If I approach 3 from the right hand side, that's like 3.1, 3.01. So 3 minus 3.1, 3.01 is going to be a really, really small negative number, but then to the 4th power, it's going to turn into a positive. 7th root, so the bottom I have a positive. Negative divided by positive is a negative, so I'm going to have negative infinity. Then I do limit as x approaches 3 from the left-hand side of a derivative of this function. So if I approach from the left-hand side, 3 minus 2.9 is a positive. 4th power, positive again. 7th root, positive, times 7, and then negative divided by positive is a negative again. So because I have both of them be negative infinity, I have a vertical tangent. Keep going on this one. Determine whether or not the graph has a vertical tangent or vertical cusp. All right, I'm going to take a derivative again. So it looks like I have to do product rule here, guys. So first times root of the second. So it looks like 1/3 x minus 4 to the, let's see, that was 1/3, so it's going to be negative 2/3 times 1 plus second cube root of x minus 4 times root of the first. So put the 6 here in the front. Okay. Since they wanted me to evaluate it at 4, it's going to be the same deal again, guys. So I'm going to fix it for you guys just so you guys can see. 6x over 3, the cube root of x minus 4 plus 6 over the cube root. Oh, it's not over in this one. It's here in the top. Cube root of x minus 4. And I thought about doing a common denominator, but since they already tell me at x equals 4, I can just evaluate it. And I can already see that this guy right here, I'm going to have, oh, by the way, this, yeah, how come you guys didn't tell me? This right here is being squared. So there it is. Now it's correct. This is going to be approaching positive infinity. So from the right-hand side of 4, and it's going to be approaching negative positive infinity from the left-hand side of 4. And this guy is just 0. As you can see, if I plug in a direct substitution 4, that's just going to be 0. So you just pay attention to this guy here. And I can see already it's going to be positive infinity for both right and left because of that square there. So vertical tangent. Hopefully that made sense. If it didn't, guys, come see me, please. Let's go to this one, which is the following is true about the graph of this. And not only do they have inflection, but it has mins and asymptotes. So let's take care of that right off the way. Before I do anything, you only have a vertical asymptote at 0. So, let's see, this one's completely wrong. You don't have a vertical asymptote at 16. So take that one out. Next, I'm going to take a derivative. F prime of x, 64 times 2, I believe that's 128. So 128x, and then remember that 16 over x is the same thing as 16x is a negative 1. So let's see, minus 16 over x squared. So there it is, and I'm going to equal that to 0 to get my critical points. So I'm going to move that to the right. So 128x equals 16 over x squared times x squared times x squared. So I get 128x cubed equals 16. I'm going to divide by 128. And let's see, x cubed equals, and 16 over 128, I believe that is, let me just do it, 16 over 128. So it's going to be 1/8. And then I take the cube root of that, and you get x equals a half. 2 times 2 times 2 is 8. So that is a critical point. So I'm going to be checking out my critical point here. So here is my f prime graph. I have a little stick at 0 because that's my vertical asymptote, and a little stick at 1/8. So if I choose a negative number like negative 10, 128 times negative 10 is a pretty relatively big negative number. 10 squared is 100. Negative 10 squared is 100. 16 over 100 is going to be a small number. So negative minus some little number. It's going to be negative. All right, so now I'm going to choose a number to the left of 1/8, like 1/10, and I just care about whether or not this here is negative or positive. So 1/10 squared is 1/100ths, but keep change flip. So 100 times 16 is going to be 1600 or 16,000. Wait, what is it? 100, 1600. And then 128 times, what did I say? 1/10. It's going to be a small number, so this guy takes over. And since I'm subtracting, it's going to be a negative, so negative. And if I'm bigger than 1/8, like a 1, I have 128 minus 16, which is a positive. So remember, you can't do anything about that 0 because that's a VA. So at 1/8, I'm changing from negative to positive, so that must be a minimum. And I notice that this one says minimum. So what you do now, you plug in a half in here and see if you get 52. And you do, because you get 64 times the half square, which is 1/4, plus 16 divided by half is 32, plus 4. And when you add all that up, you do get 52. So there it is. B is the answer. If I would have had a false statement, I would have kept going, guys, and I would have taken another derivative. All right, here we go. Now look at that. Increasing from negative infinity to 0. Let's see. Nope, you're decreasing. That's a false statement. And I would have done another derivative to see the concavity if I didn't have one that was true. Welcome back, guys. Sorry I had to take a little break. We're back on question 9 here. Ravia is upset. I think she looked at a question and was like, "What's up with this question?" So be happy, Miss Ravia. All right, so here we go. It says, "Which of the following is true about the graph of this function?" So let's take a derivative. So let's take a derivative here. F prime of x is equal to 1 plus. Let me put this in tablet mode, guys, real quick. Bear with me. All right, 1 plus 2 cosine of 2x. So I'm going to equal this to 0, and I'm going to get some critical numbers out of it. So let's see. 2 cosine 2x equals negative 1. Divide by 2, divide by 2. Cosine 2x equals negative half. Let's see, arc cosine. So then I get 2x equals plus minus arc cosine of negative half plus 2 pi n. Divide by 2, divide by 2, divide by 2. X equals plus minus, let's see, arc cosine of negative half is 2 pi over 3. So I'm going to erase this right here. So 2 pi over 3 divided by 2 is 2 pi over 6, which reduces to pi over 3. Does that make sense to you guys? 2 pi over 3 divided by 2 is 2 pi over 6. And 2 goes into 3 times. So plus minus pi over 3 plus pi n. So my critical points are pi over 3, and I guess another one would have been 2 pi over 3. Oh no, actually both of them are. So the positive one, so pi over 3 is a critical point, and then negative pi over 3 plus pi, you'll get 2 pi over 3. So here is your number line. I'm going to call this f prime. This is 0, and then this guy here is pi. And then left endpoint, that's pi over 3. And then right endpoint, that's 2 pi over 3. So now I'm just going to choose points, and I'm going to see, if I have false statements here. Those are the statements I'm going to delete. So a number is smaller than pi over 3, so maybe like pi over 6. Well, cosine of pi over 6, when I put the 2 there, it turns to cosine of pi over 3. But cosine of pi over 3 is always positive, so you know you're going to have a positive number because you're going to have this expression that's positive plus 1. Now I'm going to choose a number between pi over 3 and 2 pi over 3, like pi over 2. If I plug in a pi over 2 for x, the 2's cancel out, and you get cosine pi, which is negative 1. So then you get 1 minus 2, which is a negative number, so I'm going to put minus. And you can imagine if you put a number bigger than 2 pi over 3, like maybe 3 pi over 4, you'll get a positive again. All right. So let's see here. Let's go ahead and see what statements we have that are false. F of x is increasing between power 3 and 2 power 3. That is definitely false because I have a negative, so that one's out. It's decreasing. F of x has a local max at the point power 3. That is a candidate. We got to check if we plug in power 3 if we get this answer. F has a point of inflection. We don't know yet. F of x is decreasing between 0 and pi. That's false because, as you can see, we have many things. And F of x is concave up on the interval 0 to 2 pi, 0 to 2 power over 3. We don't know yet because we haven't taken another derivative. So it looks like letter B is plausible. Obviously, letter B is the answer. So what you do is you plug in a power 3 in here, and you're supposed to get this answer. So let's see if we get that answer, because some of you are probably starting to notice, like, Travis, I want to see you plug in this power 3. So let's plug in that power 3. So power 3, so x is power 3, so power 3 plus sine, and then I'm going to plug in the power 3, so you're going to have 2 power 3. 2 power 3 minus 1. Well, power 3 is power 3. You can't do anything about that. Plus, let's say, sine of 2 power 3. 2 power 3 is right there. So the y value is square root of 3 over 2. So square root of 3 over 2 minus 1. And sure enough, power 3 plus square root of 3 over 2 minus 1. You can't see the 1 because of the I circled into it. So there it is. Letter B is the correct answer. So I'm glad that I didn't have to go into a second derivative. And there's the answer, guys. Question 10. The graph of f prime is shown below. Which of the following could represent the graph of f of x? Hey, where's my f prime? I'm kidding, guys. I know that wasn't funny. It's over here. My apologies. So these are all f primes, I believe. Wait, hold on. The graph of f prime is shown below. Which of the following could represent the graph of f of x? Okay. So this is my f prime. And I want to know which one of these graphs could be my f of x. So what I'm noticing is that f prime is positive until I reach negative 2. So I'm going to look for a positive graph that's concave down between negative infinity and negative 2. So let's see. I'm sorry, I didn't mean to say positive graph. I'm going to look for an increasing graph that is concave down. Increasing graph until I reach negative 2, maybe. Keep going. Obviously, you already see that I circled that. Increasing graph until I reach negative 2. This one keeps increasing, so it can't be this one. That's just a linear line. It's out because I don't have a constant f prime, like f prime negative something, negative 2, negative 3. This one keeps increasing until past negative 2. It's out. Oh, okay. So we pretty much deleted all of them but one. And it has to be this one, guys. So notice that we're decreasing from negative 2 all the way to 3. So that means f prime is negative. And sure enough, f prime is negative from negative 2 all the way to 3. And then I'm increasing, and then I'm positive from 3 to 4. 3 to 5. So then I'm increasing from 3 to 5. And then f prime is back to negative after 5. And sure enough, you're decreasing after 5. So perfect. All right, guys, I hope you liked it. I guess subscribe to my channel, and let's make it a good one. All right, talk to you guys later. Bye.